Hey everyone, here we are at 5-4, so we'll see how this goes again using the book. I just want to say again that you're going to be flooded with a lot of information since we're going over so many sections a day. So the more organized you keep yourself, the better. Want to make sure that you're using 3x5 cards, which might seem an old school way, but it's very effective to go over, set them by your bed, by the TV, and just glance at them so you can see you use this one when this happens and this one when this happens. That'll be really helpful. So we're going to look at the fundamental principle of counting in section 5-4 today. Fundamental principle of counting is, for instance, when we know we have so many options of one thing, so many options of another thing, and so many options of maybe a third or fourth thing, and how we figure out what those are. So for example, let's take a look at this first example they give us here. We have an automobile available in any three colors, red, blue, or green, and it comes with either a large or a small engine. How many ways can a buyer choose the car? Well, here we have three choices of the color of the car and then two choices of the engines. So I could get a red car in large or a red car in small engine. Blue car in large, blue car in small, green car in large, green car in small. So if you take a look at this, you see you've got 1, 2, 3, 4, 5, 6 options. Another way of figuring that out is just multiplying the number of options. So if you have 3 choices of color of car and 2 choices of engine, 3 times 2 is 6. So if an operation is performed in M ways and a second operation can be performed in N ways, the total number of ways to perform the sequence of 2 operations is M times N. So if a sequence of several operations is to be performed, the number of ways to perform the sequence is found by multiplying together the number of ways to perform each operation. So again, just multiplying them together. Now, I don't know about that green. I don't think I would go for that. But anyway, using the fundamental principle of counting, let's take a look at license plate in a certain state contains 3 letters followed by 3 digits. How many different license plates can be made in a certain state? Well, for each place that we have to choose a letter, we have 26 letters of the alphabet. So 26 times 26 times 26. And for each place that we have a digit, we have 10 digits to choose from, 0 through 9. So if I take 26 times 26 times 26 and then 10 times 10 times 10, I will get 17,576,000 possible license plates. Okay. That's simple enough, I believe. Now, permutations. A permutation is a way of ordering things. So it's just another word for ordering. You know, in math, we like to pick our own words so that, you know, we can sound special. So anyway, permutation is ordering. We can count the number of permutations. We're counting the different ways that the groups can be ordered. So let's look at 5 runners running a race. One of them will finish first, another will finish second, and so on. How many different orders can they finish? If we use the fundamental principles of accounting, there are 5 possible choices for first place winner. Once the first place winner has been determined, there are only 4 left. And then once the second place winner is determined, there's only 3 left, etc., etc. So, if you want to look at the total number of ways when order matters, again, order matters, then you're going to take 5 times 4 times 3 times 2 times 1. This is 120 total ways of ordering. So in this example, we're taking a look at permutations. You can find them by what we call with this n exclamation mark here. It is called n factorial. And anytime you see n factorial, you are taking whatever number this is and you are multiplying it down to 1. So for instance, I might have 3 factorial, and that would be 3 times 2 times 1, which is 6. I might have 5 factorial, like I just did up here. 5 times 4 times 3 times 2 times 1 is 120. Okay, so that's what factorial is. We take it down to 1 and we multiply them all together. So, in general, the number of permutations of n objects is n factorial. Now, sometimes there's other stipulations that come with this, and we're going to take a look at that. So let's look at counting the number of permutations. We have 10 runners that run a race, and the first place winner will win a gold medal, second place winner will win silver, and third will win a bronze. So we really don't care, I'm sure they care, but we really don't care who is 4th, 5th, 6th, etc. So when we think about this, we want to say we start out with 10 runners. When one of them wins the gold, there's only 9 left to choose for the silver. And then there's only 8 left to choose for the bronze. So 10 times 9 times 8 will be 720. So these 3 runners were chosen from a group of 10, ordered as first, second, and third. This is referred to as a permutation of 3 items chosen from 10. Permutation of 3 items chosen from 10. And of course there is a formula for that. You can look at this and say, okay, I know that I'm only going to start with the gold, silver, and bronze and stop there. But there is a way to figure this out using a formula. And that formula is coming up. So, permutation of R items is chosen from N items as an ordering of the R items. Whew, there's a mouthful. Is obtained by choosing R items from a group of N items, then choosing an order for the R items. So the number of permutations of R items chosen from N is P, and then we put the N here and R here. So in the example we computed by the fundamental theorem of counting, we can generalize this method by using the factorial notation. If I have this, I will take n times n minus 1, etc., 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 down the line, and that will be n factorial over n minus r factorial. What does that mean? Well, let's take a look at what we looked at before. If I have 10 runners, that's my n factorial. But I am only going to give out 3 medals. So that means I'm going to take my 10 minus 3, that's n minus r, factorial. Now I want you to see what happens here. You can use a calculator to do this, but really it's not too difficult to look at. This right here means 10 times 9 times 8 times 7, and I'm going to stop there and put the factorial, and you'll see why. Because at the bottom, when I take 10 minus 3, I get 7 factorial. Okay? Notice these two will reduce. When they reduce, I'm left with 10 times 8, or 10 times 9 times 8. That's what I got over here when I was multiplying by using logic in my head down here, and I was saying, okay, 10 for possible for gold, then 9, then 8, I get 720. And you can see how the same thing can be figured out by using this formula, where n is the total number of runners and r is the total number of places that we are looking at. And in this case, it was 3 for gold, silver, and bronze. All right. Let's look at 5 lifeguards are available for duty one Saturday afternoon. There are 3 lifeguard stations. How many ways can 3 lifeguards be chosen and ordered among the stations? So this is where we have 5 total, and we're looking at only 3 stations. So in this case, we would do 5 factorial over 5 minus 3 factorial. So I have 5 factorial on the top, 2 factorial on the bottom. Again, once I get to 2 factorial, notice they reduce. So really, I'm just taking 5 times 4 times 3, and that will give me 60. They let you know that in some situations, computing the value of the permutation enables us to determine the number of outcomes in a sample space and thereby compute a probability. So with the next one, we're going to take a look at that. If we're going to take a look at the last problem, if we have 5 lifeguards, and let's say their names are Abby, Bruce, Chris, Donna, and Esmeralda. Of the 3 lifeguard station, 1 is located on the north end of the beach, 1 is on the middle end of the beach, and 1 is on the south end. The lifeguard assignments are made at random. What is the probability that Bruce is assigned to the north station, Donna is assigned to the middle station, and Abby is assigned to the south station? Well, we already know that we have 60 total ways of ordering 5 lifeguards in 3 slots. There is only one way that we're going to get Bruce, Donna, and Abby in these specific stations. So in that way, I can say that because I know I have 60 outcomes and there's only one way to order Bruce, Donna, and Abby in that order, the probability would be 1 over 60. Okay, using counting to compute probability. Here in this one, again, we're going to say that the probability that Bruce is assigned to the north station, Abby's assigned to the south station, and either Donna or Esmeralda assigned to the middle station. Well, that would mean I'm going to have Bruce, Abby, and Donna, or Bruce, Abby, and Esmeralda. These are 2 out of the 60 possibilities. So that would be 2 out of 60, which is just 1 over 30. Okay? So you do have to use some logic and think about these and look at what kind of situation you are in. Again, study, study, study. Okay, let's take a look at this one. For checker understanding, I got a smudge here. I don't like it when I get the smudges. Okay, here we go. 6 times 5. Okay, let's take a look. A committee of 8 people has to choose a president, a vice president, and a secretary. And how many ways can this be done? Okay, we have a committee of 8 people. And they have to choose how they're going to fill 3 spots. So that would be 8 factorial over 8 minus 3 factorial, which is 5 factorial. I can reduce my 5 factorials out, leaving me with just 8 times 7 times 6. Hope you can see that. 8 times 7 times 6. So when I multiply those together, I will get 336 ways that can be done. Okay? Now, looking at this exercise, let's think about this. 2 of the committee members are Ellen and Jose. Assume assignments are made at random. What is the probability that Jose is president and Ellen is vice president? Well, let's take a look at what we have here. And I'm going to use a piece of paper because my writing's a little bit too light over there. We're talking about having Jose as president, Ellen as vice president, right? Let me check. Yes. Okay. So how many ways can I do that? Well, I have Jose, Ellen, and then how many other people? 6, right? So that means I'm going to have Jose, Ellen, and maybe person 1. Jose, Ellen, and maybe person 2. Jose, Ellen, and maybe person 3. You see where I'm going here? And this is going to continue one, two, three, four, five, 6 possibilities. Notice I'm counting. 1, 2, 3, 4, 5, 6 possibilities out of the total 336. So when I do that, I will get 1 over 56 as the probability. Why did I write 54? Sometimes my brain, guys, I need a vacation. Okay, 1 over 56. All right, perfect. Now, the second part of that question says, what is the probability that either Ellen or Jose is president and the other is vice president? Okay, so what that means is I still have 6 other people besides the 2 of them. I'm going to have to add Ellen as president and Jose as vice president and continue down this line here. So you see, you got to do some thinking with these. All right, so that means now I have 12 total possibilities. So I have 12 over 336. And that will give me 1 over 28. Okay, so that's my probability. All right, and if you want to take a look at that as a decimal, because of course we're used to looking at probabilities in decimals, we have our 1 divided by 56 would be a probability of 0.017, we'll round to this place, 9. Okay, and then taking a look at the other one, you might be able to guess what 1 divided by 28 would be. It's going to be about what we looked at before, 0.03514. Okay, all right. So again, and if we round, we can just make it 1. Okay, so you can see this is about double the probability of this one, which we would assume since the bottom is double here, what it is here. Okay? All right, now let's see what else we have here. Now we're going to talk about combinations. So one of the things you really need to remember is that permutations are important when you're looking at order. So remember, permutation, order. Permutation, order. Combination, the order doesn't matter. All right? So I always think of it this way. When I go to a fast food restaurant and I'm ordering a combination platter, well, I don't care what order my items are on in my bag that I get, whether they're French fries, grilled chicken sandwich, and maybe my drink. It doesn't matter which one I get first, second, or third, as long as I get all 3. So combination, you can think of as combination platter, where the order does not matter. So when we don't care about the order, for example, we may not care which lifeguard occupies which station. In the last example that we looked at, we might just care that we have 3 lifeguards. Okay, and if that's the case, then we just call it a combination. So we will now show to determine the number of combinations of our objects chosen from n objects. Let's illustrate the reasoning with this result in 533. In the example where we showed there are 60 permutations of 3 objects from 5. And we're going to call those A, B, C, D, E. Okay, so here's our 5, A, B, C, D, E. And now we're going to look at all the permutations. You might say, why are we looking at permutations when we just said we were going to look at combinations? Well, I want to use this as an illustration to show you, here are my 60 permutations. Okay? if I don't care about the order, then ABC would be the same as ACB, and the same as BAC, and the same as BCA, and the same as CAB, and the same as CBA. These are all the same when I'm talking about combinations. My fries, my grilled chicken, and we'll say my banana strawberry smoothie. I don't care what order they hand them to me, as long as I get all three. Okay? So, whenever this doesn't matter, that means all I want to know is how many combinations are possible. I'm just looking at the combinations, which is just this top row. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 total combinations. Now, when I take a look at the formula for this, to find combinations of a set, you're going to take your n factorial, we're still using the factorial, r factorial times n minus r factorial. So you see the difference here. We're dividing by also r factorial. So when we take a look at this, for this example that we just discussed, when we have 5 things, before, when we were looking at permutations, we took 5 factorial over 5 minus 3 factorial. Well, not now. Now we're going to take 5 factorial over 3 factorial times 5 minus 3 factorial to get my combinations. Okay? So, I take a look at this, and I have 5 factorial, 3 factorial, 5 minus 3 factorial. Let's take a look at this on the side. That would be 5 factorial, 3 factorial, 5 minus 3 factorial would be 5 times 4 times, I'm stopping at 3 factorial. Why? Because I see this 3 factorial down here, so I'm going to reduce that. And then I still have 5 minus 3 factorial here, so that's 2 factorial. 2 factorial is just 2 times 1, right? So here I have my 20 divided by 2, and that's how I get my 10 possible combinations. Okay? All right, so counting the number of combinations. Here we go. Let's take a look at another example. If we have 30 people to attend a certain event, 5 of them are going to be chosen to receive prizes, but the prizes are all the same, so we don't care about the order that they're picked in. So how many different groups of 5 people can be chosen out of 30 people attending an event? Okay, that's a lot. So we have 30 people attending an event, so that will be 30 factorial over my 30 minus 5 factorial. That hasn't changed from my permutations. But now I have to add my 5 factorial on the outside because I don't care about the order. I just care about how many possible combinations there are. So when I figure this out, notice here is 30 minus 5 is 25 factorial. I always look at the bigger one between this one and this one. So I'm going to go 30 times 29 times 28 times 27 times 26. My 25 factorial reduced with my 25 factorial on the bottom. See that? And that's why I'm left here with 5 times 4 times 3 times 2 times 1. Now, if you're doing it by hand, you can start reducing these as well. Sometimes that's handy. You can reduce, 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 and then multiply. However, you will find this in your calculator. You can put these in, but it is very important that you do know the differences between the combination and permutations and how these work, okay? All right, let's look at using counting to compute a probability. In example 5.36, 30 people in attendance, we'll say we know that 12 are men, 18 are women. So what is the probability that the winners are men? What is the probability that at least one winner is a woman? Okay, so now we're going to take a look at the outcomes in the sample space for the combination. We already did this. We have 142,506 total combinations, right? So the number of outcomes in which every prize winner is a man, we're going to take a look at that. We know we have 12 men. So we have 12 over 5 factorial, 12 minus 5 factorial. Why am I using 5 factorial? Because there are 5 prizes that are going to be given. So I continue to go through here. Again, this is going to be 7 factorial. So notice I reduce my 7 factorial. I'll get a total of 792. Now, the probability that all prize winners are men would be that 792 over 142,506. Okay, so that would be very small, 0.0056. Now, if we want to know what the probability is that at least one woman will be chosen, we find the probability of the complement. Remember the complement? 1 minus the probability of all men. So if we want to look at least one woman, we're going to take 1 minus the probability of all men, 1 minus that probability that we just calculated, and we see that the probability that we will have at least one woman winning a prize would be 0.9944. Okay? Alrighty then, we are moving right along. I know again that this is a lot of information, which is why it's important that you take notes and why I'm so glad you have this video that you can go back over. So let's use counting to compute a probability. We have a box of light bulbs containing 8 good light bulbs and 2 burnt out. 4 bulbs will be selected at random to put in a new lamp. What is the probability that all 4 bulbs are good? So we have 10 total. We have 8 that are good and 2 that are bad. We are choosing 4. We don't care what order the 4 are in. So we have 4 factorial, 10 minus 4 factorial. Here we go ahead and reduce like we did before, and we have 210. To select 4 good bulbs, we must choose the 4 bulbs from the 8 good bulbs. So we want to take a look at that. 8 good bulbs. We want to choose all 4 from there. And then that would be 70 possibilities for that. So if I then want to find out what the probability is that all 4 good bulbs are selected, I'm going to take that 70 over the 210 total combinations, and I get 1/3. Okay, well, I can't believe it, but we are done with section 5.4. There's some ways here to look at doing this in your calculator. You can find under the probability section, you hit math and then probability. And we will see you next time, and we will actually be doing chapter 6.